So first of all, what is a potentiostat and why is it called potentiostat? Just like thermostat controls the temperature in your apartment or your house, this instrument is called potentiostat because it controls the potential. However, the modern potentiostat can control current too, and it is specifically designed to do a three electrode experiment. In the three electrode experiment, you have working electrode, reference electrode, and counter electrode. So the potentiostat controls the potential of the working electrode against the reference electrode. However, there is no current flowing between the reference electrode and the working electrode. The current flows just between the working electrode and the counter electrode. Basically, yeah, the potentiostats are the workhorse of electrochemistry. So that means if you are doing electrochemistry, you would use potentiostat. And there are many fields of electrochemistry, like batteries, which is really hot now, fuel cells, corrosion, coatings, sensors, electrode deposition, plating, etc., and etc. So it really covers a very, very wide applications. Uh, Potentiostat basically operates in three basic modes. First is open circuit mode. In this mode, potentiostat is applying nothing on the device under the test. It's just measuring voltage and current. In the second mode, is called potentiostatic mode. In this mode, potentiostat is applying voltage on the device under the test and is measuring voltage and current. In this case, measured voltage is equal to the applied voltage. And in the third mode, which is called galvanostatic mode, potentiostat is applying current on the device under the test and measuring voltage and current. In this case, the measured current is equal to the applied current. So you can see here, potentiostat can either apply voltage or current at a time. However, it can measure both voltage and current at the same time. Also, potentiostat can apply and measure both positive and negative voltage and current. Compare this to other devices such as power supply and load banks, they cannot do this. Although it has just three basic operating modes, it can do a number of experiments, theoretically infinite type of experiments based on the profile of the input signal. However, there are just five basic type of input signal that's in the most common use. First is your constant potential, constant current, where the signal and magnitude of your input signal doesn't vary with time. Second is pulse, where your sign and magnitude of your input signal varies in steps over the time. Third is your linear sweep voltammetry, where you are varying voltage from V1 to V2 at a certain scan rate. And fourth is your cyclic voltammetry, where you are varying your voltage from V1 to V2 at a certain scan rate and going back to V1 at the same scan rate but in reverse direction, forming a triangular profile. So when you see voltammetry, it's by default potential or voltage controlled experiment, but potentiostat can also apply similar current waveforms. And the fifth experiment is your electrochemical impedance spectroscopy, where the input signal is a sine wave. So you might ask why there is so many profiles, input signal profiles. Aren't they all just the current or voltage signals? So it turns out, depending on your input signal profile, you get different response from your device under the test. And in that way, you can study different properties of your device under the test. For example, in a capacitor, if you apply a constant potential signal, your response, your current versus time response is a sloped curve. And from this plot, you can get time constant. And similarly, if you apply a cyclic voltammetry signal on your capacitor, you get this rectangular type of waveform. And from this waveform, you can calculate the capacitance of your capacitor. So I'm just going to give you a few pointers about cyclic voltammetry right now. Cyclic voltammetry is the most popular method in electrochemistry for studying your redox mechanisms are basically your experiment setup. It has the parameters it can control during your this experiment is starting and ending voltage, which means your maximum upper voltage or minimum lower voltage, and your scan rate and number of cycles. So basically, the number of information that you can get from cyclic voltammetry is many. That depends on your experiment. So some of them are your number of redox reactions, your type of reactions, if the reactions is reversible or not, also reaction mechanisms. If you are doing ORR, you can get active surface area, etc. and etc. So as I said, I'm just going to give you a few pointers on analyzing the your cyclic voltammogram. First is the effect of capacitance. So theoretically, if it's a pure capacitor, the capacitor current is linearly dependent on the scan rate, while if for your redox peak current is proportional to the square root of the scan rate. So if you increase the scan rate during your CV experiment, the capacitive current increases at a faster rate than your redox peak current, such that at high scan rate, your capacitive current can totally dominate your redox peak current. So this means your peak analysis becomes difficult. So during your CV experiments, it's very important to optimize your scan rate. And also for your peak analysis, very important to normalize for your capacitive current. Second is IR compensation, which is a little difficult subject, but I'm gonna present here anyway. So what happens when you apply potential on your working electrode versus your reference electrode is that the working electrode doesn't experience all the potential that's being applied. So there is some loss of potential, and this loss of potential is dependent on the current that's flowing and the uncompensated resistance, which is the resistance between your reference electrode and working electrode. And this relation is given by Ohm's law. That means if your current is high, then you're going to have more voltage loss. So for example, on your figure on your right, so you can see the reaction rate, K, is fairly fast, and you have 10 ohm uncompensated resistance. So if you increase your scan rate, so the current magnitude also increases. That means your voltage loss also increases. So in this plot, you can see there's a systematic shift in peak potential. Compare that to your figure on your left, you can see it's a very slow reaction, but there is no uncompensated resistance. So, but you can also see here that there is a systematic shift in peak position. So without compensating for your RU or your uncompensated resistance, here you can see you can get a wrong or inaccurate analysis. So IR compensation is very important for both qualitative and quantitative accurate analysis of your CV. And in most potentiostat, you can do this easily, including that of Squidostat from Admiral's instrument. So the third pointer is that you can get various mechanistic insight by simulating or modeling your CV. And also depending on the reaction mechanism, you can get different profiles. For example, here, I've given your EC reaction mechanism where your electrochemical reaction is followed by your chemical reaction. So A is reduced to B and B turns to C. As you can see, at 10 millivolt per second, you don't see any reduction peak. That means, and this peak represents that of an irreversible reaction because all of the B is turned to C. However, if you increase the scan rate, now the electrochemical reaction becomes faster, but the chemical reaction becomes same, so that most of the B now can turn back to A instead of C. So in this way, by simulating your CV, you can get various mechanistic insight. So in summary, the the methods in electrochemistry gets their name by the profile of their input signals. And the device under the test gives different response based on different profile of the input signal. And as for CB, you have to normalize your capacity effect for proper analysis of your peak. And I cannot stress this enough, but our composite is very both qualitative and quantitative analysis, and model and fitting reveals deep insight. So thank you for your thank you for listening to my talk. And if you have any question, I'll answer at the end of the